Is Mr. Clay Bavor, Vice President of Virtual Reality at Google. Clay joined Google in 2005. Most recently, he led the design team for Google's most popular applications, such as Gmail, Google Docs, and Google Drive. He created his first VR project at the age of 12 with HyperCard. He was one of the creators of Google Cardboard and has led Google's VR project since 2014. Today, he will speak on how virtual reality can enhance the human experience with the title of Enabling Rich and Immersive Experience in Virtual Reality. Please welcome Mr. Clay Bavor.
Thank you so much. Good morning. It's great to be here. Again, my name is Clay, and I lead the teams at Google focused on virtual and augmented reality. And as someone from outside the industry, but who depends on the work that you do to build products, and who has a huge amount of respect for what you all do, it's a real honor to be here. So I thought I'd talk about three things this morning. The first is how to think about VR and AR. These are terms thrown around a lot, sometimes interchangeably, often in the context of competition, which will win. Some thoughts on how I think about it. Second, what's Google doing in VR and AR? And kind of what can you depend on us to do and push forward? And then third, a bit of a deep dive on some challenges and opportunities in displays in VR and AR. Can you raise your hand if you've tried one of the high-end PC-tethered VR systems? So it looks like about half. That's pretty good. So for everyone who hasn't, I want to share with you an experience that we walk first-timers in VR through in our offices. And this happens in a conference room in Mountain View. And we call it the diving board experience. And it starts here. You're kind of poolside. It's clearly not real. If you look at the ground, you can see that it's kind of made of this weird white grid. And you look to the side, and there's some diving boards. And you say, what is that really tall thing? You look up, and you look up, and it's about 150 feet up. And you know what's happening next, right? So we push a button, and you're teleported up there. And people lower their center of gravity. That's what we've evolved for millions of years to do if we find ourselves on a cliff face. We've modified controllers so you can actually see your feet walk out to the edge of the board. And we ask you to go to the edge and step off. And most people can't. Most people can't do it. And we remind them, hey, you're in a conference room in Mountain View. Everything's cool. Don't worry. And they can't do it. What's going on here? So this, for me, captures some of the magic of VR. It drives your senses in a way that you feel completely present, completely transported somewhere else, in this case, at the top of a diving board. And so VR can kind of put you anywhere. It can take you anywhere and really make you feel like you're there. So augmented reality, on the other hand, this shown here is with a mobile-based device, can bring digital information and using your context as surroundings, integrate digital objects and computing into the environment you're in. Right? So AR can kind of bring anything to you while maintaining your presence in the environment you're in. So VR can take you anywhere. AR can bring anything to you. And now this is important. It's not VR versus AR, kind of which will win, which is better. They're not two separate and distinct things, but kind of rather two labels for points on a spectrum. And for lack of a better name, I call it the immersive computing spectrum. So at the left end of the spectrum, where it's all real reality, this, right, you're just here, right, that's the left end. At the right end of the spectrum, where everything is computer generated, everything is digital, you have virtual reality. And somewhere in between, you have augmented reality, others call it mixed reality. The terms don't matter so much as this idea that, again, these aren't separate, distinct things, but rather different flavors of immersive computing. And the important underlying concept with immersive computing is that it enables us to experience computing more like we experience the real world. It kind of makes computing work more like we do. And this idea of computing that works more like we do is fundamentally why I believe AR and VR are going to matter a lot. If you look over the arc of computing, from punch cards to touchscreens, right, every time computers got easier to use, computing became more accessible, and we became more capable, more powerful with it. And I think VR and AR push that a level further, again, by letting us take in computing just as we take in the real world, and letting us interact far more naturally with our hands, with our eyes, and time. So we think it's going to be a big deal, and we want to push it forward. So what is Google doing in this space? I think about it in kind of three different categories. Platforms, apps, and then building blocks, these kind of enabling technologies that enable people to build new kinds of devices or new applications and services. So let's start with platforms. So Cardboard, Google Cardboard was our original platform, right? And the insight with Cardboard was, if you look at a smartphone, it has some sensors, an IMU, an accelerometer, a high-resolution screen. Well, if you look at a VR headset, what does it have? Some sensors, a high-resolution screen, but also some lenses. So Cardboard was the easiest way to get some lenses in front of these high-resolution displays to give people kind of a glimpse of VR in a low-cost way. Today, it's more widely distributed than any other VR device by an order of magnitude, right? There are well over 10 million of them out there in the world and growing quickly. So we started there. Last year, we announced this thing called Daydream. It's our platform for mobile virtual reality. And the idea was, rather than kind of tricking smartphones into becoming VR devices, build them from the ground up for VR. And so Daydream was composed of a smartphone spec, so-called Daydream-ready phones, low-level changes through all parts of Android to reduce latency, a really important part of VR, and then an SDK and tools for developers to build on. To get this whole thing kick-started, we released what we call Daydream View, a headset made by Google. You slip a phone into it, and it's super comfortable and really easy to use. And that got things started. Today, there are almost a dozen different Daydream-ready phones, and we expect there to be tens of millions of them out in the world by the end of the year. At Google I/O, just last week, we added to this idea of smartphone-based VR a new category of devices, something that we call standalone VR headsets. And standalone VR headsets integrate everything that you need for VR into the headset itself. So you don't need to hook it up to a PC, you don't need to drop in a phone, there are no cables, and it's far easier to use. And of course, when you build everything for VR, you can optimize everything for VR. The displays, the optics, the weight balance, and so on. And then running atop all of this, both the smartphone-based devices and the standalone devices, is a really nice user-visible layer of software. Think of this as kind of your desktop for VR. This here is called Daydream Home. It's kind of the home world you start in. And from there, you can jump off and into apps, into VR video, and so on. So that's a quick update on what we've been doing in platforms. In apps, of course, Google has a lot of apps that kind of naturally bring themselves to VR. So Google Earth, we turned into a VR version of Earth. So not only can you fly over a city, but you can actually feel as if you're walking through it at kind of Godzilla scale and peer down and look at the Transamerica building or the Golden Gate Bridge or Half Dome or any place else on Earth. We also built an amazing educational tool called Expeditions that enables teachers to take their classes on virtual reality field trips. And then one that's, I think, really, really special and captures this idea of computing that works more like we do is an app called Tilt Brush. And Tilt Brush lets you, in essence, paint in 3D space with light and paper and fabric. And rather than try and describe it to you, I thought we could just show you a video of some of the things you can do with it. So if we could roll the video, please. tilt brush, and we're seeing it used in just some incredible ways that we never expected. For designing clothes, which you saw there, you can basically paint with fabric instead of stitching a prototype together. Designing cars, creating entirely new forms of art. People are actually now creating entire kind of interactive movies and games using it. Again, because you can just get an idea out of your head at scale using your body in the way you've lived your entire life using it, right? Using space as context, and it's very, very powerful. So that's apps. The last area we've been making investment in are these building blocks, these kind of enabling technologies that make new categories of products possible, or which can make it far easier for a developer to build something. One that we just announced last week at Google I/O, that's our annual conference, is something we call WorldSense. And WorldSense enables what's known in VR as positional tracking. And what that means is that in a VR headset, not only can you look around you, but you can also move in space. You can lean in, you can lean back, you can dodge, you can move all around. And that makes the whole experience far more immersive and far more comfortable because the virtual world is responding accurately to your movement in space. Now, what's cool about WorldSense is, unlike some other systems that use installed cameras or sensors, WorldSense relies on sensors that look out into the environment and basically uses distinct visual features in the environment to triangulate its position, kind of like this. And as a result, you can use it anywhere, and yet the world perfectly matches up with your movement in space. And this is going into the standalone VR headsets that we're working with both HTC and Lenovo to build out later this year. Another building block we've been working on is a system called Jump, as in jump to Paris, then jump to Machu Picchu, jump anywhere on the Earth. And at its core, Jump is a tool for capturing real-world VR content. The insight here is there's a lot of interesting stuff happening in the real world, but the tools for capturing it, digitizing it, and then distributing it in VR, we found were really lacking. And so we built a system that consists of cameras, processing software, and then playback on YouTube and other vehicles to make it work. We've been working with camera companies like GoPro. This is a camera from Yi Technology, a Chinese-based company that makes amazing action cams, and also IMAX. And the work we do, the most important work we do, is software that runs in a Google data center and ingests footage from 16, 17 cameras and is able to seamlessly merge them all into VR video that's 3D all around you, and yet has no seams or artifacts where we've kind of stitched the different video streams together. So these are just two examples of building blocks that we're working on and we're trying to push forward. But of course, to create a VR system or an AR system, there are so many other things that we need as well, other building blocks. And so what else needs to get better? Well, the short answer, unfortunately, is basically everything. Basically everything needs to get better. These devices need to be lighter and lower friction to get in and out of. All of the enabling technologies need to get better. Tracking needs to get better. Input needs to get better. Displays need to get better. We'll talk about that. And then more content and experiences. Just to give you an idea, right, this is a handful of just the fundamentally unsolved problems in VR and AR. And just to deep dive on a couple, 3D reconstruction. In VR, you're going to want to pull in a photorealistic model of the environment you're in, perhaps other people you're with, so that you can modify that environment, maybe turn it into a game space. Or in AR, you'll want to digitize an object and be able to take it with you and insert it realistically, convincingly into an environment somewhere else. GPUs and rendering. Depending on how you do the math, we are between 5 and 7 orders of magnitude off from being able to, in VR, walk through something like a Pixar movie. Right? So we just need dramatically more compute and more efficient ways of rendering and driving displays. And then we're at a displays conference. So the displays themselves, they need to go so much further. And dynamic range, varifocal displays, size, luminance, resolution, field of view, all of these things need to get much, much better. And I'm going to focus just on VR here. And within VR, just 2 problems, because there are a lot of problems and it would take a while. And that's scale, enabling more displays to be VR capable, and then visual quality, the visual fidelity of the scene that you experience in VR. So starting with scale. So our goal with Daydream was to really make VR accessible for everyone. And of course, smartphones were a key part of that, right? If you can unlock this kind of latent superpower in a smartphone with a simple headset, you can turn any smartphone into a VR device. But that superpower is only possible if you reduce what's known as motion to photon latency to under about 20 milliseconds. Motion to photon latency just means the delay between when you move your head and when the picture updates to reflect that motion. And optimizing that latency was a key focus of Daydream. We worked on rendering pipelines, reading sensors, and of course, displays are key in this. And the common wisdom is that only OLED is capable of the kind of fast response times and low persistence that you need for VR. But there's a problem. Okay, 70% of smartphones shipped in 2016 shipped with LCD. So it puts a huge part of the market off limits for VR-enabled devices. In particular, developing markets. And think about it, we in more developed markets take for granted having large flat panel TVs in every room. In developing markets, right, a VR experience may be the first immersive display that a person or family has owned. So I think this is really important to get right. So to give you an idea of what a high latency display looks like, what high motion to photon latency looks like, this gives you an idea, right, where you move your head, the picture takes a while to catch up. What's not shown here, which also happens on traditional LCD, is blurring, right? You basically get frames of the environment which are supposed to be locked relative to you, blurring together. So not only is it not as real seeming, for some people, including me, it can actually be very uncomfortable. It feels like motion sickness. So the ideal looks something like this, right, where your head motion is instantly reflected in the display. And so we wanted to know, okay, can LCD do some of the same tricks as OLED? Fast response time, low persistence. And it turns out the answer is yes. We've been working with partners to overcome these challenges, and in particular, I'm really excited to announce that we've been working with Sharp to create a smartphone LCD for VR. And we focused on two areas in particular, response time and persistence. So first, response time. So current LCD panels for smartphones have response times already in cases, depending on what you're transitioning between, north of 20 milliseconds. Right? And remember, the end-to-end system latency needs to be 20 milliseconds. So we've blown our entire latency budget on just the display alone. It's not going to work. So our goal here was to achieve 6 milliseconds. That leaves enough time in the rest of the pipeline for reading in sensor data, for doing scene composition and rendering. And through a bunch of tricks, we were able to get there. And the response time curves look much more like this, all below the 6 millisecond threshold. This is a big deal, big deal. But we still need to solve the persistence problem. Right? And what happens in traditional smartphone LCDs is you have an always-on backlight. And the problem is, this can result in all this blur, because as you're moving your head through the environment, you're illuminating the image even as pixels are still transitioning. Right? So you get overlapping frames, and sometimes that's tolerable on a smartphone or a TV. In VR, it makes the world look like a total mess and introduces other artifacts as well. So great solution, strobing backlight. Cool. So this reduces blur, of course, because you're illuminating pixels only after they've settled and finished transitioning. But there's another problem. You have to wait until all of the pixels have been scanned out to do the strobe. And so by the time the last row has been scanned out, the first row of pixels is a couple milliseconds old. So you're losing a couple milliseconds here. So we pushed this further and introduced a rolling strobing backlight. Right? And the idea here is you illuminate portions of the panel only as they're scanned out, meaning you minimize the latency between a pixel arriving, being scanned out, and actually being displayed. Now, combined, the progress we've made on faster response times, lower persistence, dramatically increase the quality of LCD for smartphone VR. And we're really excited about the improvements and the kind of things it's going to open up for us in scaling Daydream and bringing VR to far more people via smartphones. So thanks so much to Sharp for a great partnership on this. We're really excited about what's ahead. So we talked about scale. Let's talk about visual fidelity. And in particular, acuity and field of view. Two things that if you've tried a VR headset, you want more of. You want more of both. So how good do displays need to get? What should we shoot for? Well, helpfully, a bit over a year ago, in very early April, we created a concept video for a product that we think demonstrates many of the attributes that we're going to need in kind of the perfect VR headset. And so if we could roll the video, please.
The things that make virtual reality compelling have been with us for tens and hundreds of thousands of years. At its core, it's about storytelling. Everything along the way is a step towards trying to get more immersed in the experience and more immersed in the story. But, we're still putting something between you and the world.
What we really wanted to do was to make something feel real. And so this is the first headset for actual reality.
Perfectly.
What's realer than real? Probably nothing. Or maybe something. I doubt it, though. I think we're done.
So that was obviously not a real concept video. That was our April Fool's joke of 2016. But this idea of an actual reality headset with 20/20 vision and a wide field of view, that's actually what we're going for, right? We're not going to be done with VR displays until when you're in VR, it just feels like this. It feels like you're there. It feels completely real. Bonus points, obviously, if it's waterproof and you can surf with it, and there are dogs and stuff. So let's actually ground ourselves, though, in where we are. Like, how far do we need to go? And for that, we'll pull out the trusty eye chart. So normal vision, 20/20 vision, just means at 20 feet, you see what a person with perfect vision or corrected vision sees at 20 feet. So legally blind is 2200. Eye chart looks about like this. You can kind of only make out the top letter. In most states in the US, in order to drive, you need to have 20/40, 20/50 or better vision, or you need glasses. You're only allowed to drive during the daytime. So today's VR headsets, well, you're not quite legally blind, but you definitely couldn't drive. 2100, right, depending on the specific headset. So we're a long way off. And just to give you an idea of how far off we are in something that you might do most days, the newspaper. Newspaper with good vision looks like this. If you tried to read it at arm's length in a VR headset, it would look something like this. You can kind of make out the big headlines, but that's about it. So we're not doing so well on the acuity front. We got a ways to go to that actual reality headset. So let's look at field of view. Now, it's obviously hard to simulate field of view on a 1080p projector, right? But typical human field of view is about 200 degrees, but past 180. We have amazing peripheral vision. You can do a test with a friend. You can see all the way out here, depending on your bone structure and eyes and so on. And it's pretty neat, but today's VR headsets are like this, in the best case, about 110-degree field of view. It's a bit like tunnel vision. So if you want to increase acuity or increase field of view, or both, we need more pixels. We need way, way more pixels. And just to anchor us in where we are today, today's best consumer available VR displays are about 2 megapixels per eye. And of course, that's spread over those 110-degree field of view. That's why you end up with 2100 vision in them. And well, we'd like more pixels. We'd like more pixels. Push acuity, push field of view, push both. And so I'd like to let you in on a secret project that we've been working on. We've partnered deeply with one of the leading OLED manufacturers in the world to create a VR-capable OLED display with 10x more pixels than any commercially available VR display today. It's capable of delivering 20 megapixels per eye. That's the pixels of 2.5 4K TVs, shrunk down to about this size. We're really excited about it. Of course, I can't simulate what a 20 megapixel display looks like on a 1080p projector. But to give you an idea of the relative increase in acuity and field of view that we're going to be able to drive with this display, we can take this, and we can sharpen it to this. Acuity goes here. Oh, and by the way, we can more than double the field of view, right? And take it all the way out here. And I've seen these in the lab, and they're spectacular. It's indeed way, way more pixels. And it's not even what we're going to need in the final display, but it's a very large step in the right direction. So amazing, great, we have this awesome VR display. No, actually, it's kind of horrifying. And the reason is the math. The math is horrifying. 20 megapixels times 90 frames per second or 120 frames per second times 2 eyes, you end up with data rates of 50 to 100 gigabits per second. And not only can you not render that much data, you can't even transfer it. You can't even move it around the device. Rough. It's rough. So what are we going to do? What's the solution here? Well, human physiology comes to the rescue. Despite how we perceive the world, which is, wow, it's so high resolution and crisp, and I can see everything so well, our optic nerve, the nerve that connects our eye to our visual cortex, is actually very low bandwidth, about 10 megabits per second. Right, so you have 50 to 100 gigabits per second, and yet the thing connecting our eyes to our brains, 10 megabits per second. Turns out this is going to be helpful in VR and AR displays. And it's going to be helpful because of a technique that we refer to as foveated rendering. Foveated rendering uses cameras built into the headset to track your eyes, to figure out what you're looking at. And what we can do is render very high resolution where you're looking, right, where your fovea, that's the center of your retina, which is very high acuity. You can render full resolution there and then drop off, right, at the periphery. And you can dramatically increase rendering efficiency, dramatically reduce the amount of data that you need to move around. And so this 20 megapixel display, along with advances in optics and other technologies, and then approaches like foveated rendering, it's one of the ways that we think we're really going to be able to push forward this visual quality, visual fidelity in the VR experience. And we're really, really excited about it. So, VR and AR. We talked about kind of two different flavors of immersive computing. Again, computing that works more like we do. And I shared some of the investments we're making at Google in platforms and apps, in these kind of technical building blocks. And then a couple steps forward in displays for VR, enabling far more smartphone displays to be VR capable, and then really pushing the limits of visual quality with this OLED display. So hopefully the challenges here and the opportunities ahead excite you. I know that for many of you who've been in this industry for some time, focusing on advancing television displays, smartphones, automotive displays, and so on, VR and AR can seem very new, maybe a bit out there. And the question, of course, is when to start investing, right? When to start building. And if you've ever been surfing, you know that you need to start paddling well before the wave starts to crest if you're going to catch the wave. You watch the water, you kind of look out into the ocean, you look for kind of rises in energy, kind of everything lining up. And I spend my days reading the waters, seeing if everything is going to line up, seeing when that energy is really going to start to build. And so here, with VR and AR, I will just say now would be a really good time to start paddling. Thank you so much. Thanks for having me.